Alright, so I'm gonna explain some stuff for the first quiz tomorrow. I think this will help me. I don't know if I'm gonna share this, but I think this should be very helpful, especially if you're a little lost like me, trying to understand everything. Anyway, so for the first quiz tomorrow, I know 100% I felt a little bit lost with the Thevenin equivalent because I haven't done it in a while, but the easiest way to explain it again is you have kind of like a voltage divider circuit here with another resistor. This is not negative 48, by the way, this is just 48. This is the positive and negative terminal. I'm sorry about the weird. Anyway, so you have your voltage source, and we're trying to look for V Thevenin, R Thevenin. Pretty simple, right? You'd think. But it is, don't worry. So for this circuit, you have current flowing, voltage at these nodes, and then you have your current flowing out. But keep in mind, I don't know if you guys remember from circuits, but current does not flow out of this resistor, and so we can cut it off here, and we're left with a voltage divider, which can let us find the Thevenin. So we get 48 volts times our 4K ohm resistor, and that's because the 4K ohm resistor, this terminal has the same voltage as this, and for your Thevenin equivalent, you're always going to want your V Thevenin to be what comes out of your circuit. So keep that in mind. I know that it can be a little bit confusing, but just remember that, you get your voltage source, and then your V Thevenin is going to be whatever you get out of it. And so we do the little, multiplication here, and these two are in series, which should be pretty obvious. We get 12 volts, and then we come back to our original circuit, and we have these three resistors, which to find the equivalent resistance, we're going to want to short out our voltage source, kind of like we're taking it out. So voltage sources are short circuited, and then current sources are open circuit. And so these two are going to be in parallel because this is going to be a wire connecting them from two ends. So this is going to be parallel, and then these two in parallel are going to be added together with the 8K, which is going to give us 11K ohms. And just a little quick addition, remember that this is how you add, that's not supposed to be there, sorry. 12, and then 4K ohm, and that should give us 11K. But that should be how you're doing that. Sweet, okay. So we get, this is our result. This is just a little review of Thevenin equivalent, just because it, like I said, I revisited it and it was a little bit weird, but it should be pretty standard for what we're gonna cover next. So just note for this that all resistors are added and voltage source is shorted out, or if you have a current source, like I said, open circuit. And then in this case, we used a voltage divider to find V Thevenin, but that can change depending on what circuit that you have. But if we're given a circuit like this is going to be the procedure, and I don't think we're going to solve more complex circuits like this, because we're not in circuits 1 anymore, and I think we should have a pretty general understanding of how this works, because we might be applying this in increments, not in one huge problem all about this. So that should be important to note. And then I know this will definitely be covered on the quiz tomorrow. It gave me a little bit of a hard time. But this is a non-ideal voltage source. Now, an ideal voltage source, you're going to have your power supply or your DC source or whatever connected to a resistor. That's going to be ideal. This is a non-ideal, which means that you have your voltage source in series with a resistor, which is in series with your output resistor. This is non-ideal. This is a voltage divider, which is not an ideal voltage source. So, what do we need to know about non-ideal voltage sources, because we dealt with them in this lab? So, easiest way to put it, we can think about it kind of like a system where you're flowing in this case, voltage, and then you are outputting another voltage, right? But we're putting something else into the system, which is the DMM. Sorry about the shitty handwriting, but you get the gist. That's how I'm gonna explain output resistance, which is gonna be the output resistance being outputted by our power supply, because our power supply is putting out voltage. And then our input resistance, we're introducing something into the system. So we have our R out in this case. So I know it can be a little bit confusing, because at first when I was writing this down, I had switched these by accident. But output resistance, think about it like you're outputting it from the power supply into the circuit. And then input resistance, you're introducing something. So introduce, input, output, power supply. I think that's the best way to memorize it, at least for me. And then in the lab, we had some trouble because we were not getting the voltage expected when we were plugging in our voltage source and then putting our two resistors in series, and it just wasn't working out like it was supposed to. This is because we had loading occurring, and loading, like I wrote down here, happens when you connect a device which changes your voltage or your current, and this is because of your output resistance or your input resistance. And the most ideal case for no loading to occur, for basically a damn near perfect circuit that we're expecting, we need our R out, so what's coming out of our power supply, to be almost 0 ohms. And then our DMM, we want it to be infinity. In this case, because we're measuring voltage, and that allows for no loading to occur. So how do we write basically a general rule of thumb for that? So the best way to explain it is you have your R in, so what you're connecting into the system or your circuit or whatever, you want it to be as big as possible, and then your output resistance to be as little as possible. So you're going to want to follow this rule right here. So to avoid loading, you're going to want R in to be way bigger than your R out. And that's basically all you got to follow to not encounter this loading evil. And so how do we find our input and our output resistance? See, I just messed up there, and it needs to be very carefully thought out. So how do we measure these? We basically create a voltage divider like we did in lab, and then we add a load resistor to it at the end here. So it would basically be like that. And then we are going to test different resistors, and the one that basically gives us our V out as half the value. So we're putting in, let's say we're putting in, I don't know, 12 volts. And when it comes out as 6 volts, that means that whatever resistor you used as your test is going to be the exact same to your DMM if you're looking for your input resistance, let's say. So like we were doing in lab, we were using a 10 ohm for the test. I don't remember if that's what it was, but when we use this, we built the voltage divider. 10 M. God, sorry. Anyway, built our voltage divider, and once our voltage and our output reached our half our voltage here, like I said, 12 and then 6 here, that is when it is equal to what we tested it with. So the DMM in this case would be 10 ohms because mega ohms because of these two being equal. So that's, I know it sounds like a lot to cover, and I bet half of you guys or more got it, but I had to, I don't know, make this to understand it myself and explain it and teach myself. And like I said, I don't know if I'm going to share this video, but I think if people find it useful, then I will probably be doing this for the lab and the lecture, and then maybe for another class. I'm not sure yet. I have a lot on my plate this semester, but I think this was useful for me, and I hope it's useful for you as well. And yeah, let me know if you have any questions, or I'm not a professor or anything, so maybe don't come to me, but Dr. Inan or Dr. Hoffbeck. But if you have any questions, I'm always free to answer them, so let me know. Thanks.